So a couple sections ago, we saw an integral that looked heinous. It was some sort of like type 2 triple integral, and it had like square roots all over the place in the bounds of the integrals. And we figured that that integral had some symmetry along the y-axis, so we should use something like polar coordinates, but in 3 dimensions. And those polar coordinates in 3 dimensions are precisely what we call cylindrical coordinates. So what are cylindrical coordinates? If you've never seen cylindrical, this is how they work. Suppose I have a point. I'm going to draw some sort of like box to describe this point right here. Okay. Then the way we describe in cylindrical is drop it to the xy plane. Here is x, here is y, here is z. One way to describe it is use polar coordinates in one plane and then just leave the other coordinate alone. Okay? So what we do is we draw, or we give to the point in the xy plane polar coordinates and then just leave the z coordinate alone. And remember that for that, we had the radius to the projection of the point. We have the angle. This radius is not the radius to the point itself. It's not the distance to the point. It's just the distance to the origin to the projection. When we do spherical coordinates, we will replace this by also the distance to the origin itself, and we'll give 2 angles instead, but that is in the future. So, so this point that was x, y, z will be given in cylindrical coordinates by radius. That's the distance to the origin of the projection. Angle, that's the angle of the line to the origin with the x-axis, and how high up it goes, z value. The z value stays. So that's a different way of describing points. When do we use this? When it has some sort of like cylindrical symmetry, so it has some radial symmetry with respect to the z-axis. If my shape had symmetries along the y-axis, then I would use polar coordinates in the xz plane and then leave the y coordinate alone. Or if it had symmetry along the x-axis, rotational symmetry in the x-axis, then put polar coordinates in the yz plane and leave the x1 alone. Okay? It works in all 3 directions, but for the sake of this class, I think we're going to stick to cylindrical coordinates in this. So you can always rotate your figures and have them have the symmetry in the z-axis. Okay. So how do we convert from one coordinate system to the other? Through the equations that are here. Well, from r and theta to x and z, that we do like we did in polar. If I know r and theta, I can get x and y, as x is r cosine theta, y is r sine theta. If I knew the x and the y, and I want to know what the r and the theta is, x squared plus y squared is r squared, so then take a square root. Or y divided by x, that's the tangent of theta, take our tangent and you can find what theta is. What point has cylindrical coordinates 2 pi 3, negative 2 for x? How did you figure that out? Oh, yes. So what we did is that x is r cosine theta, y is r sine theta, and z equals z. Before I use those formulas, that's great, just plugging in the formulas. But before I do that, let me sketch what's going to happen. They tell me the projection of my point is 2 away from the origin. So if I draw a circle in the xy plane of radius 2, it has to be somewhere in that circle of radius 2 in the xy plane. And the angle has to be pi from the x-axis. So if the angle is pi, I have to go from here, do all the way here because it has to be pi. So the direction I have to go is in that direction and 2 away, so it has to be here. So what I call my projection, this sort of like empty dot, has to be there. Now I know the position in the xy plane of the projection, and now use my z value, has to be 3. So if I now go 3 up, 1, 2, 3, and I draw, the point itself has to be up here. So it has to be, what point is that? The x coordinate is -2. The y coordinate is 0. I'm in the x line. The projection is in the x axis. So this is 0. And the z coordinate has to be 3 as advertised. Okay? But I can do what was suggested, which is use r cosine theta. R is 2 times the cosine of theta. The cosine of pi is -1. So it has to be -2. R sine theta, the sine of pi is 0. And z equals z, so it has to be 3. So it has to be -2, 0, 3. Find the cylindrical coordinates of the point 1, 0, 0, 0, 0, 1, and 1, 1, 1. So here is my first point is 1, 0, 0. If that is the point, this point has, first of all, z coordinate 0. That doesn't change. It is 1 away from the origin in the projection and itself, but in the projection to the xy plane, we're 1 away from the origin. And the angle to the x-axis is 0. So it actually looks exactly the same. 1, 0, 0 looks the same in Cartesian or in cylindrical coordinate. All right, 0, 0, 1, it's up here. That one will have 0 radius. By the way, when I have 0 radius, the angle itself, it's not well defined, because if you go back to the formulas that I have here, these formulas only work when the x coordinate is non-zero. If the x coordinate is 0, then the angle is automatically 0. So I'm going to call this angle 0, and the z coordinate is 1. Look at that. It's exactly the same point again, in Cartesian or in cylindrical coordinates. But now 1, 1, 1, let's see what's happening there. Here's the point. Here's the projection. So now I have something more interesting. So what is the distance to the origin in the projection? It is a square root of 2. So the distance in the projection to the origin is the square root of 2. The angle, it's in the diagonal, so the angle has to be 45. And then the z coordinate stays the same, so the z coordinate is a 1. So that's how you convert from Cartesian to cylindrical, cylindrical to Cartesian. Okay, let's describe now a whole surface. What is the surface given in cylindrical coordinates by z equals r? So z equals r means that if I am at any distance from the origin, the z coordinate will be the same. So every time so if I'm here, then the point will be here because the radius is 0, so that point has z equals 0. Now, if I am 1 away from the origin, then the z coordinate will be equal to the distance to the origin. So it will be all the points above it at height 1 are also in the shape. If I go this far from the origin, then I will be that high, that much higher in the shape. Okay? So what happens is that it's actually going to be a cone like that. How can I figure that out without my amazing drawing skills? Well, I have a formula, z equals r, but I know what r is. R is the square root of x squared plus y squared. Okay? Or if you square both sides, I get z squared is equal to x squared plus y squared, which is, this is one cone. This is a double cone. But notice that I can't have z being negative because the radius cannot be negative. The radius is always positive. So I don't really have the lower part of the cone, of the double cone, in my shape. So it is a cone. If instead of had z equals r squared, then what happens is that, well, I'm going to have what shape now? This is going to be z equals r squared, which is x squared plus y squared. So now what I get is a paraboloid. Okay, so now I get something like this, a paraboloid. Okay, but see that they both are shapes that have symmetry, rotational symmetry about the z-axis because they are given in cylindrical coordinates. All right, so now we want to integrate, do those integrals. We would have the usual integral would be of this shape, would be the integral, the triple integral. The innermost would be the z integral. And then we have to figure out how to replace this double integral. And this is the double integral we have to replace by a polar coordinates integral, which we knew how to do. We can replace to polar, but we have to remember to translate everything to r and theta, and we have to multiply by the conversion factor. Okay, so there is a conversion factor that you have to multiply to be able to translate to the cylindrical coordinates, which is the same as in polar coordinates, so nothing new to be learned here. Okay, so let's try to do that with this integral. So first of all, what is this solid? This solid is below the z equals 4 minus x squared minus y squared. X squared plus y squared is a paraboloid opening up. With the negative sign, it's opening down and lifted up by 4. So this paraboloid looks like this. Okay, and this height is 4. Now it has to be above the xy plane, so it has to be above here. So what is going to happen is that that's going to cut my paraboloid there, and what I'm trying to integrate is within that paraboloid and above the xy plane. So z is between z equals 0, which is what this means, and the other z value. This has rotational symmetry about the x-axis, so it's a perfect candidate to do cylindrical coordinates. I need to know what is the shape of the projection. Okay, so what is happening here? That is given by z equals 4 minus x squared minus y squared, and z equals 0. So all in all, I get x squared plus y squared equals 4. So it's a circle of radius 2. So I want my base is going to be all the points of radius up to 2. So that tells me that in polar coordinates, the base is r theta with r between 0 and 2. This is 2 squared. That's where I got a 2. And the theta goes all around. If they told me this is cut off by some planes, I would have to compute some angles. But here, I'm going all around. So the theta is between 0 and 2 pi. Okay? And the z value is just going between those two functions. So what I'm trying to integrate then is going to be, remember in polar, we started with d theta between 0 and 2 pi. The radius is going between 0 and 2, so that's my dr. The z values are going between 0 and what? I don't want to write x and y's anymore. I have to translate them to thetas and r's. Let me give myself more space, the r d theta. I'm going to translate 4 minus x squared minus y squared. Luckily, x squared plus y squared is r squared. So this is 4 minus r squared. So it's going between 0 and 4 minus r squared. That is the z. And I'm integrating, not 1, and not computing the volume. I'm computing the integral of x squared. So x squared, I have to translate x as r cosine theta. So this is going to be r cosine theta squared. That's how I translated x squared over there. And I have to multiply by my conversion factor. Okay? So all in all, the inside of the function is r cubed cosine square of theta. That's what I have to integrate. In the polar coordinates, the z coordinate stays the same. The polar coordinates are r theta z value. So the z doesn't change in any way. When the symmetry is about the z-axis, the z stays the same. Okay, so let's do the integral. I have to integrate from 0 to 2 pi, 0 to 2, 0 to 4 minus r squared, r cubed cosine square of theta, dz dr d theta. With respect to z, this is the integral from 0 to 2 pi, 0 to 2. There is no z value there, so this is just r cubed cosine square theta z dr d theta between 0 and 4 minus r squared. So that is going to be the integral from 0 to 2 pi, from 0 to 2, 4 minus r squared, r cubed cosine square theta dr d theta. Remember that if I have a function, I'm integrating with respect to r and theta, but this is a function of r times a function of theta. I can actually break it up as a product of two integrals. So this is the integral from 0 to 2 pi of cosine square of theta d theta times the integral from 0 to 2 of, I can distribute that r cubed to be 4r cubed minus r to the 5 dr. And it turns out that that integral with respect to theta, you can use this. I think we've done it before, in fact. Using that, this integral is in fact pi. Okay? So this is going to be pi times, the other one is going to be r to the 4 minus r to the 6 divided by 6 between 0 and 2. So that is pi times 16 minus 32 over 3, which is 16 over 3 pi, all in all. So that's the answer. So all we did is we changed the x and the y into polar, multiplied by the, that's the most important part here, is that to set it up, I have to multiply by my conversion factor. And then it's just an integral in 3 variables, z, r, theta, and then just integrate like we've done before, iterated integrals.